Watch a physical, autonomous system try to navigate a complex environment. It moves swiftly, hits a dead end, and sparks out. The trajectory fails. In the digital realm, modern LLM frameworks extend an agent's capabilities using structured packages of procedural knowledge. These are typically organized around a skill.md file, loaded directly into the agent's context, shaping how it plans, uses tools, and edits code. But when an agent fails a task with one of these skills loaded, the developer faces an immediate engineering problem. You cannot automatically conclude the skill caused the failure. The failure could stem from base model variance. The verifier might be narrower than the actual task specifications, or the baseline task might simply be impossible for the agent to solve in the first place. Benchmarking aggregate pass rates across a platform does not solve this. Without a reliable way to isolate these confounding variables, engineers are flying blind when a newly added skill breaks a system that previously worked. Researchers from HUST, UIUC, and Microsoft devised a way to algorithmically isolate skill-induced failures. They imported a classic software engineering concept into AI evaluation: differential testing. Their rigid testing architecture uses two parallel execution lanes. Every confounding variable is frozen. The task, the verifier, the repository state, and the LLM itself are locked into both the target lane and the reference lane. Only one variable changes. The target run receives the specific skill being audited, while the reference run receives either no skill or a matched alternative. The reference run acts as a pseudo-oracle. It does not need to execute a perfect solution. It simply needs to pass the verifier under those frozen conditions. If the reference run passes and the target fails under the exact same constraints, the failure is definitively localized. The injected skill caused the break. Scaling this differential method to over 20,000 paired comparisons, the researchers isolated two distinct classes of operational failure. The first is the functional failure. This occurs strictly when the target run fails the verifier while the reference run passes. The second, more subtle class is the efficiency regression. In these cases, both the target and reference pass the task, but the target run incurs a massive performance penalty. This chart maps out the strict mathematical threshold required to qualify as an efficiency regression. With the token ratio on the x-axis and execution time ratio on the y-axis, the first requirement is that the minimum of either ratio is greater than 1. This eliminates runs that merely trade token length for execution speed. The second requirement is that the maximum of either ratio must exceed 2.0. By requiring at least one cost metric to strictly double, the methodology filters out standard run-to-run inference noise. These strict thresholds ensure the resulting dataset represents unambiguous, high-confidence harm. And the data from these confirmed cases completely dismantles conventional engineering assumptions. The first major engineering misconception is that an LLM agent fails because a retrieved skill is entirely irrelevant to the task. This proportional chart visualizes the 125 confirmed functional failures in the dataset. Look at the data for applicability mismatches, skills that were genuinely irrelevant. They account for a statistically insignificant 1.6% of all failures, just 2 cases. The dominant cause is entirely different. Almost 69% of all functional failures fall under a category called task implementation faults. A task implementation fault happens because the agent systematically overtrusts a skill, precisely because it is topically relevant. The agent reads the skill's reusable guidance, the generic defaults, the templates, the isolated examples, and incorrectly elevates them into mandatory task-specific requirements. This manifests in 2 ways. The agent implements a required code element using the wrong API or value because it blindly copied the skill's template, or it omits a required element entirely because the skill's generalized workflow happened to bypass it. The perfect semantic match makes a skill dangerous. Irrelevant information is simply ignored by the model. High relevance breeds fatal overconfidence. Looking at the 182 confirmed efficiency regressions reveals a second major misconception: the belief that a skill's cost is dictated purely by the number of tokens in its markdown file. This stacked bar chart breaks down the 182 efficiency regressions. Prompt length is not the primary culprit. Over 62. This means the loaded skill forcibly elongates the execution trajectory, turning optional exploration or simple coding tasks into mandatory, exhaustive verifications and heavy rebuild pipelines. Now, look at the 25. To understand the operational impact of these findings, we have to look at the difference between an ad hoc prompt failure and a packaged skill failure. This split screen shows the mechanism of reuse. An ad hoc prompt fails once, but a skill is a fixed framework configuration. If a skill misbehaves, it biases the agent and fails exactly the same way every time the system automatically retrieves it for a matching task. Because they are reused, skills act as structural liabilities for agent platforms and marketplaces. They require continuous automated screening, such as the study's skill triage taxonomy tool, to extract differential evidence and catch boundary cases before deployment. As agent frameworks scale, a loaded skill cannot be viewed as a free capability boost. It is a highly volatile, costed configuration decision. The study's findings translate into 3 strict authoring rules. Rule 1. Always cleanly separate mandatory task constraints from reusable examples and defaults within the prompt structure, so the agent does not mistake guidance for obligation. Rule 2. Keep the always loaded main body text short. Purposefully push checklists, long templates, and background material behind explicit lazy loading triggers. Rule 3. Condition any verification or testing guidance on the task's budget and the code change size, rather than prescribing exhaustive testing loops by default. To maintain scientific rigor, we must note the exact scope of these findings. These proportions were measured using the OpenCode harness with Claude Opus 4.6. Different models or ecosystems will exhibit different specific variances. Furthermore, the differential testing method contains a deliberate coverage bias. Because the framework requires the reference run to pass, this dataset captures only failures where the base agent was capable of succeeding on its own. Agent skills are powerful enablers for impossibly hard tasks, but if improperly packaged, they become active, systematic liabilities for the easy ones.